Hi friends, welcome back to another video. My name is Neo and I am a master student of AI study in Leuven, Belgium. So in this video, we're going to talk about a very popular topic in computer vision, which is the convolutional neural network. In this video, we'll mainly talk about the theory behind this network. In the next video, we will actually show you how to build a convolutional neural networks in Python with Keras. Please consider to like and subscribe to see more content like this. Like neural network, the convolutional neural network also has its biological origins. This origins is actually from the study of the structure of the visual cortex in mammals. It reveals that the neurons in the visual cortex actually has a small local receptive field. It means that a neuron will only process a very local area of what we actually see. So this idea inspired an artificial neural network structure which becomes CNN. The first convolutional neural network is implemented by Jan LeCun in 1998. So this is actually the diagram of these architectures. From the left, we have input images, which is 32 times 32 by pixels. And then we have one convolutional layer. Right after that, we have a subsampling layer. And again, we have another convolution and subsampling. Then it follows up as a fully connected neural network with an output dimension of 10, so which corresponds to the digits from 0 to 9. So before we discuss the components of the convolutional neural network, we want to first revisit some concept. So first, the concept we would like to talk about is the tensor. So tensors are n-dimensional array we build up to. So we have the example of scalar, vector, and matrix, and the tensor here. So it is very convenient to fit sets of images into models as tensors. So we have the dimension like IHWC, where I stands for the number of the images, H stands for the height of images in pixel, W stands for the width of images in pixel, and C stands for the color channels. So for gray images, it is 1, and for RGB images, it is 3. So before we talk about the convolutional neural network, we also know that the fully connected neural network can also use for tasks like classification. But why bother we need to use convolutional network? This is because we have the following challenges for the fully connected network when it comes to images. First of all, the number of the trainable parameters will increase drastically with the increase of the size of image. For example, the Minis dataset was 28 times 28 pixel, so you have an input of 784. However, for images with 256 times 256, which is quite normal nowadays, it will result to you about 65k parameters. So another big limitations of the fully connected neural network is that it can lose the spatial features of an images. So spatial features refers to the arrangement of the nearby pixel. In an image, the pixels nearby to each other are much more correlated to each other. CNN has the following advantage for dealing with images. First, it can capture the spatial features. Each layer will look at an increasingly larger part of the image. CNN also gain invariance by having units only connect to its nearby pixels. And CNN also can help with the regularization, limit the search of the weights to the size of the convolution. So now let's talk about the convolutional layer. Let's start with the input layer, which is the images. So the convolutional layer are only connected to the pixel in the respective field. So when you have the input image here, so you can see that for each values in the convolutional layer, it actually only relates to a local part of the input images. So the second layer will do the same, but now it's only looking at the values in the convolutional layers. For the edge neurons, there might be not input for them because it will actually looking at the area which is outside of the input. So to solve this problem, we will introduce padding. So that is basically just tends the input images with a layer of zeros, and then we can perform the convolution for the edge neurons. So the picture on the left side shows an example of a picture with a padding size of 1. So now let's take a look at a convolution example. So we have images here with a size of 5 times 5 pixels, and we have a filter of 3 times 3. There is no padding size in this case, and we have a stride of 1, 1. Stride 1, 1 means that when we are moving the filter in the images, if we move horizontal or vertically, we will only move the kernel by 1 pixel. So now here we get our first values in the convolved features, which is 4, and then we just continue, slide the filter to the right with a pixel of 1, and we get 2 as a second value, and then we move it to here, and we have 3. So now we are done with the horizontal, so we need to move vertically for 1 pixel size, and now we get the value of the second row, which is 2, and so on and so forth. So by the end, when we finish the scan of the whole images, we'll get our convolved features. The output size can be calculated with the following formula. Output width or height is actually equals to the width and height minus the width and height of the filter plus 2 times padding size, and then divided by stride, and then plus 1. So you can see a calculation of the output size in our example. So now let's talk about the pooling layer. So the pooling layer will subsample the input images, which will reduce the memory use and computer loads, as well as the number of the parameters. So this is often applied right after the convolution, and we get our convolved feature map. We can apply a max or average pool with a filter size and stride, so that the only max and the average value can be moved to the next layer. You might wonder what is the output size after pooling. Actually, the formula from the previous slide still applies. You can calculate the output after the pooling. So now we talk about dropout. So dropout is a common technique deployed with CNN to prevent overfitting. So it can be treated as a form of regularization. So during the trainings, the units are randomly dropped out along with their connection, and it prevents the units from co-adapting too much with each other. So here are some famous convolutional neural network architecture. So each year the number of the layer is increasing drastically. Of course, with more layers, we are able to process more complicated data than just recognize the digits images. So that concludes the overview of convolutional neural network. In the next video, we will build the first CNN, which is by Leuven, and we will use it for image classification. I hope you found this video helpful. Make sure to like and subscribe, and I will see you in the next one. Bye bye.